Welcome to the course MTH 305A. Here we study the differential geometry of curves. Already we have defined parameterized curves. Okay, so this is page 1. So, already we have defined uh, parameterized curves. So, definition. Then we have given many examples. Then also we have given the definition of trace, tangent, speed, and unit speed curve. So then we have defined regular curves, uh, arc length, unit speed curve. Then we have studied reparameterizations. So in reparameterizations, we have shown that every regular curve admits unit speed reparameterization. So unit speed reparameterizations. So next we study curvature. So before going to the definition of curvature straightforward, so before that we study some preliminaries. So some preliminaries, namely orientations and vector products, vector or cross product in R3. So in this video we discuss orientations. Okay, so today's topic is orientations. So this is page 2. These are done. So today's topic is orientations. So this is page 2 of vector spaces. Finite dimension and over the field real. Okay, so let us consider uh, V be a vector space of dimension V, vector space over set of all reals, and this is finite dimensional vector space, and dimension of V, suppose dimension of V equal to n. Okay. Well, let us consider E equal to E1 or EI, where I lies between 1 and n, and f, this is equal to, let us consider two bases. So E and f equal to small f I, where I lies between 1 and n. So be two bases of V. Then so E, suppose E1, so E1 is an element of V, and f is, so f is, this is a basis of the vector space V. So we can write E1 as a linear combination of the basis elements in F. So we can write E1 equal to a 1 F1 plus a 1 F2 and so on, plus a n1 Fn, and this is equal to summation a I 1 Fi over I equal to 1 to n. Okay, for a I 1 belongs to R. So these are scalars for every I lies between 1 and n. And similarly, E2 equal to a 1 2 F1 plus a 2 F2 plus and so on, a n2 Fn, and similarly you can write this as summation a I 2 Fi over I equal to 1 to n for some scalars a I2 belongs to R and I lies between 1 and n. And in general, for j, you can write Ej, this is equal to a1j f1 plus a2j f2 plus and so on, a n j fn, and which is equal to summation, in short this is summation a I j fi I equal to 1 to n for scalars a I j belongs to R. Okay, so and we write box E j, this is equal to the column vector so with the entries or the coefficient of this linear combination a I, so this is a1j a2j and so on a n j, this is column. Okay, so next page is page 3. Now we define matrix A whose jth column is A is n cross n matrix whose jth column is box Ej, that is A equal to the matrix A 1 1, this is the first column, A11, A21, and so on, AN1, and second column is A12, A22, and so on, AN2, and the last column, nth column, that is A1n, A2n, and so on, ANN. So this is a square matrix of order n cross n. Okay, and this is a fact that determinant of this matrix A is non-zero. So it is fact because E and F they are basis. Okay, so A is basically change of basis matrix. So it is a fact that determinant of A is not equal to 0. So that is either determinant of A is either positive or negative. Okay, so now we are ready to give the definition. Definition. So if determinant of A is strictly greater than 0, then we say that the bases E and F are equivalently oriented, or E and F have the same orientation. Okay, so then we say that the bases E and F are equivalently oriented. Or in other words, E and F have the same orientation. Okay, so this is definition 1. Now consider the set of all ordered bases. So two ordered bases. Now consider B of V. This is the set of all ordered bases of the vector space V. The set of all ordered bases of the vector space V. Now we define a relation on the set B of V. This is page 4. Okay, so here we define a relation on the set B of V, that is the set of all ordered bases of the finite dimensional real vector space V. Okay, by following E related to F if and only if they have the same orientation, that is if E and F have the same orientation. Okay, so this is a relation on B of V. So here we have the following exercise. Show that this relation is an equivalence relation. So that this is an equivalence relation, and moreover, and there are exactly two equivalence classes. So there are two equivalence classes. So now let O1 and O2 be the equivalence classes of the relation SIM be the equivalence classes of the equivalence relation SIM. So we assign plus sign to one equivalence class plus sign to O1 and minus sign to the other equivalence class O2. Okay, so and so now definition: if some ordered basis E belongs to O1, then we say that the ordered basis E is positively oriented and if E belongs to O2, then we say that E is negatively oriented. Okay, so before stop we note that the standard ordered basis of Euclidean space of dimension n is assumed it is positively oriented. Okay, so the standard ordered basis, that is EI, where I lies between 1 and n of Euclidean space of dimension n, is assumed or considered positively oriented. Okay, so that is the equivalence class O1. This is equal to the equivalence class containing, so suppose this is E. So the equivalence class containing the standard ordered basis, the equivalence class of E is assigned plus sign. So this is a convention. Okay, so we stop here.